Okay, for the introduction, I have you already, some of you have already familiar about the part, about the compressor. So some question that we will discuss today is about the fluid friction inside of the part. I think some of you already have demonstration in the experimental, so it's gonna be related to the one where we need to define clearly what laminar and turbulent flow based on the Reynolds number and calculate the pressure drop and also the couples. And for the application, we will discuss also about the series and parallel part. So maybe you already understand that the series is we combine all of the head losses in the one line. So you have if you have pipe flow in the series conditions, and for the parallel, the head loss must be similar between line A, line two, so line one, line two, and line. But the must be direct combinations. Okay, let me start. Before we start, do you have any preference for questions we need to start for the session? If no, I will discuss in order, from one until we will have to one. So we start from question one. We have a pipe connecting A and B. We don't know where is the direction. So the information available is about the diameters. It's around 6 centimeter. And it's contained glycerin with a density of 1.26 1,260 kilogram per meter cubics. Flowing with the flowrate, it's already defined. The flowrate is 8 meter cubic per hours. And we need to define laminar and turbulence. And we need to define the direction, the flow up or flow down. And the last is we need to define about the effective flows. Right? And we assume that the pressure of 1 atmosphere, so this is the information about the 1 atmosphere, 2.7, 2.1, and 1 atmosphere can be taken equal to around 1 bar. So we need again, we call again about the equation of the Bernoulli equation. So I hope you already familiar about the equation that we can combine here. First, defining about the Reynolds number, we already have the Reynolds number is density multiplied by velocity divided by viscosity. In other case, because we already have understand that Q equal to velocity multiplied by area, so it's going to be U velocity. Okay, this is the Q, so we can change the velocity equal to 4Q divided by E. So you can change for especially for the circular pipe, we can change Reynolds number from the normal one to as the function directly as the function of debit instead of using velocity. And from the debit, we only change from 8 meter cubic per hour to meter cubic per second, just divided by 1 hour is 1,600. So we can get the Reynolds number is 4. So the 40 is laminar or turbulent. Reynolds number 40 is laminar or turbulent. Laminar. Because it's less than 2,300 Reynolds. So it's going to be categories laminar. And the next is the direction. So because we know that point B has the higher elevation and also higher pressure, of course, the flow will coming from B to A. And the head loss we take from these equations. We have losses. losses will must be equal to energy contained in the pipe system. So because of the change of the pressure, change of the velocity, or change of the elevations. In this case, we have change of the pressure because this is higher than 1 atm, this is also higher than 1 atm, or is it different level, not in the reference point where we have the elevations. And the second is the elevation is different. So we have change of the elevation, change of the pressure. But for the velocity, we again need to know that this is incompressible flow. It means the density is going to be constant. So because the mass volume is constant, it's mean A because density is constant, incompressible flow. And the area, is area constant? It depends on your cases because this case we already know that pipe is uniform pipe with the constant diameter. It means the area also will be constant. So the velocity gonna be constant. So we can relate the change of the velocity because the velocity is constant. So we can derive this. So the losses will be equal to the change of the elevation and the change of pressure. Any questions? Okay, we can continue to question 2. The next is about water with the temperature 20 degrees Celsius, given the properties, density and viscosity. And the pipe is 600 meter long pipe with a diameter 15 centimeters, and the flow rate is 6 meters cubic per second. The head loss is 50 meters, so we need to estimate the pipe roughness in millimeters. And if the roughness is double, what will the percentage increase of the head loss? So the head losses is depend on the factor this one. So we already have the equations of the head losses in the strike pipe. This is the equation for head losses minor. We have two head losses, major and minor, because this is categorized in the strike pipe, so we can include the minor losses. Minor example into 10, 12, different exits, turning point, and anything that not strike pipe. So strike pipe is the minor losses. And we can change the equation of losses minor to find the fixed. So this is the multiplication from this equation. To find the velocity, we input this equation that will derive from equation of the flow rate. We have the velocity equal to 3.4 meter per second. Because we have already information about the velocity. You already know V is 15 centimeter, length is 600 meters. Velocity is from here, gravity, you know, and losses is defined 50 meters. So we can get fluid the friction factor equal to 0.021. Okay. Any question? So far? No?
And why we know difference? We thought use formula from the rate also.
This one? You?
Yeah. Is it from the rate? Is that really
This one? This is from the equation of Gibbons.
Oh.
Because the Gibbons is velocity multiplied by area.
Always.
So area is the cross sectional of the pipe. This is the visual area. So we can use for ED. Anything else? Okay. Because we already get the free frictions factor, so we can using the Moody chart. So first, because we need a Moody chart, we need to find. Oh, sorry. This is turbulent because the Reynolds number is 5.1 and 25. So this is the turbulent regions, and we need to get the width of f 0.0212, and Reynolds number is 510 divided 10 power 3. So we have this one. To get the, sorry, I will show you to ensure that you understand. So in this case, we have informations for how to see the Moody chart. This is the, I take from your slides. So ignore this sign, the purple, blue, and the orange. Previous one, we already defined that Reynolds number is 5.1 times 25. So this is the Reynolds number, 5.1 times 25. Line. And the next, we also know from the frictions is 0.0212. So this is the friction. This is the. So we have this. And we need to find about the relative roughness. Because there is this relative roughness is the stroke line. And about this line, this is around between 0.001 and 0.00. So in advanced calculation, because this is the scale, sometimes we need that or something, so it's still applicable. We conclude that back to previous one, we conclude that rapid process is zero one position in between 0.01 and 0.0. Okay, so we have the relative. Because we have information D is pretty good. So the roughness is 0.2. And dropping the roughness, it's mean we double from 0.2 to 0.4. It will with the same diameters and with the same Reynolds number. We have from the from this case, we only change from 0.1 to 0.2, and we will change the friction factor to be 0.024. So the percentage increase will be 20%. Yeah.
Is it okay for questions to box the density of value?
Oh, yeah. Yeah. You can use 998 or 1000. It's not used to the but can we create 100 so Yeah, what is the chance? Yeah. Oh, yeah. Yeah, yeah, this is the meters. Yeah. Yeah, we calculate the relative roughness. Now we calculate the roughness from 0 to 0.4. Roughness calculate. And it will change the relative roughness from 0.15 to 0.2. And the same kind of number, 5.1 and we get using this line. So we take a line from this one to. So for practice 1, 0.0212, and this is 0.02. But you think and then about because we will always use modifier to find higher losses of the resistance for turbulent. Because for the laminar, you can take equation 64 divided by Reynolds number. But for the turbulent, we need to use and this is the area of the turbulent.
How did you get the blue line?
Blue line.
Yes.
This is from slide in your lecture notes. So I just take it to express ignore this one because I only use this.
I only create. Okay.
But I cannot erase the learn from the sorry for
Wait, sorry. Because there's no like
something that in this case we have to know this 0.021 and 5.1 and 5. We can predict 0.01 and 0.2. I think 0.001. For calculation, but we know is 3 variables. So we need to 2 nodes and 1. I don't think this factor or we have to talk about yeah. Okay, the difference is this is for the smooth part and this is for the temporary box. For the smooth part, this is unstructured. So you find that's what the rest department will be like. What is the smooth part is It's not equal. Oh. Oh, this new fit of filtration powder. Where if it takes the roughness from 0, have the new so we compare new add with the old. So we get the proportions, but we take from the new one, from this. This is the old one where we have the reactive parameter is 0.0015. The friction factor is 0.0.
Yeah.
The new one is we double the reactive parameter from 0.015 to 0.002. So this one is large, but the number is same constant. So we have the new line of the friction factor is 0.02. This is not from interpolations, but from reading from yeah. Yeah. Yeah, it's make like what name? This is yeah, I know this is making you confused because I just take from the side, but again, this is like making what's the name? Making problem. So you minimize the total number. So this is you should take this one instead of this one.
Wait, so 0.0015 correct?
Sorry?
So it should have been 0.015?
Yeah. 0.01.
Okay, so then how does that? The math really makes sense.
Right?
The rough.
This is the in meters. Yeah, sorry. To make it, this is in meters and this is in millimeters. So if you multiply, this is non-unit and this is in meters. And the same millimeters.
No, because
It's a fixed 0.5.
yeah.
For the participation. Anything else? Okay. Now I will continue to the next. The next is question 3. Yeah.
Sorry, I have
To move the chart or the question?
4 months. No, as in the moon chart.
Yeah.
So why do you need both values? Why can't you so the value that we got was 0.00.
Yeah.
You has the vertical line done.
Or the provided the random numbers.
Yeah, it's the random number. Why is it done then?
This one, this follow.
Oh, right.
So this is sorry, the horizontal line is then Practical one for the number and perfect for the
Oh, no, it is. They don't just want to do one, and do something to one file and the file of the section.
pattern for the movie chart. Alternatively, there are many digital movie charts that you can find in the internet. So you only put the height fixing cover or the numbers here, so you can get the movie. But the easy, I don't know, is it available for the exams between the but for the Facebook exams, normally they can provide you the movie chart, so you need to read it manually between the tool and then at the column and you get the. But in practical, I prefer using the available online source for the movie chart. Just input two names and then get one. Okay, number 3, we have two reservoir, which split is the ethyl alcohol at 20 degrees Celsius. And the tank are very wide. The meaning of very wide is it has height in this area. So this is just simplification. The meaning of the wide is we have very long and very wide. So the volume will not be changing. Instead of there is flow from the top reservoir to bottom reservoir. Because if there is a change of the elevation, your calculation is going to be quite difficult. So it assumes that the tank are very wide. It means the elevation from 0.1 to 0.2 is going to be constant. This is why they say the tank are very wide. Assume that the flow is laminar, so we assume it's going to be laminar, neglecting minor losses. So we, after we have two losses because of the entrance and the exit, so that but they ask to neglect the minor losses. So we only focus on minor losses. It's mean because of there is pipe with diameter 2 millimeters. Find the flow rate in the cubic meters per hour, then check if the initial assumption is correct. So initial assumption is the flow is laminar. So we need to check is it truly laminar or not. Then we say that it is laminar, but we need to prove that this is correct assumption. Okay, so this is the equation. So from this equation, we need to know first is about the location of the elevations. So this is the elevation of location 1 and location 2. Why we choose this line instead of this line? Because we need to eliminate the pressure difference in the equation of Bernoulli. Bernoulli calculates the losses based on the change of elevation, the change of pressure, and the change of velocity. Because we want to eliminate some unnecessary function. For the example, the change of the pressure. So if you choose the location 1 and location 2, location 1 and the location 2 in here, the atmosphere, the pressure is atmosphere. So we can eliminate the change of pressure. So we only need to find the from the Bernoulli, we only focus on the change of elevation. So the change of the elevation will be equal to the losses in the system. And the losses is coming from the Mayer losses. So this is equation from the Mayer losses. And we can change the velocity. The velocity we change with these equations. U equal to 4Q divided by T squared, because this is the pipe is circular pipe. We have we can derive this because U squared it means U squared means U squared divided by T squared Q. And input to and the next is because there's assumption that the fluid is laminar, so we can assume again this is the laminar, the smooth part. So the fluid friction, we don't need to check in the movie chart that you see directly with it. Now, slide introduction. I think I put it in the reference that friction for the laminar is 64 divided by the number, and friction for turbulent in the smooth part is roughly. And we input the real number, so we see that the mu and change the mu with the figures. So we get this. So because we have information, this is F. We input to losses equation. We input that is and we take the Q on the equation. We get Q is function of C and F because F losses equal to total different allocation is 0.9. From P density velocity, then from that this is the viscosity, this is the right comparison, and losses because of average. Please be note that the strength of the allocation is 0.3 because this one is 0.5 plus 0.4. We have to replace the allocation 0.5. But for the length of the pipe is from here, so 0.4 plus 0.8 is going to be 1.2. Okay. And the next is to check is it true laminar or not. Just input to the log number because we have already get information about the Q, the flow rates. So we can get the log number is something and multiply. So it's going to be true that this is laminar. So the assumption is if the assumption is not correct, so you need to choose again with the correct one. If this is the turbulent, so you need to find the new equations for the friction, the turbulent, and input again to the equation. Okay. Any questions for participants? Yeah. You can just smooth charge or the just question if it is smooth part. In the case it is smooth part, so you can use application.
For the animation.
All that things. So this is the for the smooth part, this is for the laminar, and this is for the this is for and if it has roughness, I would think you need to use fully because this is assumed smooth. And next is number 4. We have the pumping system with the efficiency is 70%. Deliver water at 20 degrees Celsius from one reservoir to another 7 meter higher. So this is from low to high elevations. The piping total length is 20 meters with diameter of 5 centimeters, and the roughness is 0.15. So it means you need to do a multi-charge calculation again. And the mineral losses is from 2 bendings with R per D 1.5. So not only mineral losses because of the pipeline, but we also need to calculate the mineral losses due to the 2 bendings, one bending and the second bending, plus the entry energy. So the losses minor is lining system, the minor coming from the entrance, 2 bending, and exit. So in this calculation, we have the information because using the Bernoulli equation again, we can get that the losses is gonna be similar with the energy from the pumping minus the elevations, and this is the total losses in the system. So it assumes that this is the losses in your system because of the minor losses, and this is 3 plus 3 is minor losses because of entrance, exit, and bending. From the table, we already have that entrance. This is your reference. The entrance is 0.5 and exit is 1. And for the bendings, you can pick from this line. Well, the information available is R per D equal to 1.5. R per D is here, 1.5. And the relative roughness is 0.002. So it's going to be about this one. So this is the relative roughness 0.002. And we take vertical line to get value of T. So K is 0.45. This is how we get the information of mineral losses because of the bending. For the enter and exit, we can get directly from the constant 0.5 and 1, but for the bending, we need to take from distance. And a question for how to get information about the mineral losses key factor for the mineral losses. Okay, because we already get 3 information and 3 exit and bending for the value of K. And then the next is we need to find the information for the minor losses. For the minor losses, sorry, I can back here for the minor. This is information from the tabel and this from the chart. Okay, that's fine. The next is we need to find what is that. Again, we need move the chart. So we need information of Reynolds number. This is the
What is turbulent?
sorry.
You the E or the D.
Yeah. For people, rapid flow. This is the blue line. Because the level contact is 0.38, and in 0.02, you can see the last the while I make on the line, and every person will be classified, and then the right, and take the other to the right to find okay, from the Renault, we have 2.8 10 to 5, so it's gonna be turbulent. Please do your own calculation using the multi chart. Input the Renault number 2.8 10 to 5 with the relative forces or epsilon per d is 0.03, and then you can find the F equal to 0.027. Using the similar with equation number two. Yeah.
You didn't bring like small lines parallel to the three line.
Yeah.
That ground.
So from the movie chart, we have F equal to 0.027 and input to your equation. This is we know what is because entry. This is because the axis one, and this is because two bending. Because the bending is diagonal to 0.45 into the value 0.9, and this is friction because of the Maillard loss. Alberti. And this is the friction coupled from the distance. We put together, we have the head friction equal to 21 meters. And the next is questioning about the pumping power. So from the pumping power, we need to input the head pump itself. From the head pump, using analogically, this must be equal to head of friction plus head of the elevation. Because they need to increase the energy from to the increase of the elevation and increase the energy to fight or to how to say that, to eliminate energy coming from friction. So it's gonna be the total of goods head. Okay. So we have 28 meter for the head pump, and the pumping power itself is 4.3 kilowatt. Don't forget to define the efficiency because this is already explained in the beginning that the efficiency is 0.4. It's gonna be higher than the required or the ideal pumping. Because this is the ideal pump. And this is the actual pump. So we need to define that. Anybody? Yeah.
Previous slide.
Sorry?
Can you go to the previous slide?
If you saw. Sorry. Yeah.
So just before we go to the plates.
Oh, yeah. Oh, yeah. It's on. Yeah, it's on. So, revisions from number 3. Thank you for the revisions. So you need to calculate this equation. This already. Yeah, you do have to start transforming this equation to this equation. Well, so this will move 0.1 from the previous from your party. So you will get a new reform. Anything else?
What is the power formula?
Sorry?
What is the power formula?
You mean number 4? Yeah, this is the strength of the this is the mass flow rate multiplied by mass flow rate multiplied not mass flow rate. This is the pressure given multiplied by the head. This is pumping power. Pressure is because the head elevation pump. So we have GH.
That's change.
Anything else? Yeah, that's fine. Thank you. Okay, for the last, I think because it's already time to one, so this is by I think it's gonna be uploaded by Alex. It is I don't know, uploaded by White, but we upload by him. So thank you for coming today, and see you next to. So,